Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at polarity, which is another way of talking about how evenly electrons are distributed in a molecule. And so not too surprisingly, we do need two big understandings. First, how electrons are spread throughout a bond, and second, how the molecule itself is structured. And so one of the big uses of polarity is this tells us a lot about how these electrons are distributed through a molecule, whether evenly or unevenly. If the electrons tend to gather at one end of the molecule is said to be polar. It has a negative pole and a positive pole, depending on the exact structure of the molecule. So for example, if I'm looking at lithium hydride, hydrogen wants electrons a lot more, so it'll have a lot of electrons. Lithium will have none. And hydrogen fluoride, the fluorine has all the electrons, the hydrogen has none. And because these electrons gather unevenly, this will end up having some pretty significant impacts on reactivity. Conversely, we have molecules where the electrons are spread very evenly, such as hydrogen gas, at which point the molecule is said to be nonpolar because there's no collection of electrons on one end or the other. Now, before we kind of look at the polarity of a molecule, it's really important to look at the polarity of an individual bond, because after all, molecules are made of a whole bunch of bonds. So if two atoms have very similar electronegativities, then both atoms want the electron the same amount, so the electron ends up being fairly evenly spread. So think of something like hydrogen. Hydrogen gas, each hydrogen wants the electron as much as the other one, so it ends up being spread quite evenly. If I have something like hydrogen fluoride, there's a large difference in between the electronegativities, so the electrons tend to gather on the fluorine and spend less time on the hydrogen. So that means that anything that relies on the presence of electrons will tend to occur on the fluorine end. And if electrons are going to enter the molecule, they're much more likely to enter from the hydrogen end. And this tends to dominate a lot of trends of reactivity. And it's worth noting that the difference in electronegativities can grow to the point that this bond really is less polar and more ionic. So you can imagine something like hydrogen fluoride. Fluorine wants those electrons so much more that this bond is really teetering on the border of ionic. And one of the ways we can evaluate this, as we've addressed previously, is electronegativities. So if our electronegativity differences are less than 0.5, even though the electrons may gather on one end or another, we tend to call the bond relatively nonpolar. So for example, carbon and hydrogen are kind of sitting right on the edge of a nonpolar bond. And arguments could be made either way for a carbon-nitrogen bond. However, if you're somewhere between about 0.5 and 2, then we have a full-on polar bond. And one of the things that makes carbon quite cool is with an electronegativity of 2.5, pretty much everything forms a polar bond. The only exception being hydrogen, and maybe nitrogen, make some arguments for phosphorus and sulfur, but generally, carbon makes polar bonds with about everything. But that also means that carbon doesn't tend to form an ionic compound with anything. Because once we have an electronegativity difference of about 2, then the electrons are firmly on the more electronegative element, and we have formed a full ionic species. So we're going to be mostly looking at species that sit in this kind of happy medium range. So we'll be talking a lot about carbon and species like nitrogen and oxygen, because they're very good at forming these polar bonds. So once we have the polarity of an individual bond determined, now we have to figure out how the arrangement of multiple bonds may have an impact on molecular polarity. So let's say I have a whole bunch of polar bonds, but if all of my polar bonds are symmetrically arranged, then the electrons are pulled evenly in all directions. So as a net, the electrons don't tend to gather on one end or another. So let's take a look at boron trifluoride. So fluorine is much more electronegative than boron, so it'll pull all the electrons out here to the edge. But if you look at the direction of these poles, each one kind of counteracts the other. So the outside of boron trifluoride is very rich in electrons, and the middle is very poor. But the electrons haven't gathered on one end or another. And as a result, boron trifluoride is actually nonpolar. However, in contrast, if the bonds aren't radially symmetric, then the molecule tends to become polar. So let's take a look at something like water, which looks a lot like boron trifluoride. I just have removed one of the bonds. And in this case, oxygen is pulling all the electron density from the hydrogens. So all the electrons tend to gather on this end, and they tend to be depleted on this end. And so we end up with net negative on this pole, net positive on this pole, and turns out water is actually quite polar. So just because you have polar bonds doesn't mean you have a polar molecule. However, as soon as the molecule isn't completely symmetric, you can start getting this gathering of charge on one side or another. Now, when we're talking about the polarity of a molecule, this is often measured using something called the dipole moment. And there are several ways of calculating this, but a good way of looking at it is it's going to be looking at the difference in electron density from one end of the molecule to another. And let's look at another two examples of this. We have carbon tetrachloride. So all of the electrons are going to gather on the chlorine and are going to be removed from the carbon. But because of this, what we end up with is an even distribution of electron density around the edges, and it isn't being pulled from one side to another. So this is measured using the dipole moment, which says no net dipole, no net collection of charge on one end, and this is measured in dBi. So this is that capital D. So if you are a not completely nonmolar molecule, you have a dipole moment of 0 dBi. However, let's go ahead and replace two of these chlorines with hydrogens. Now the chlorines are going to move the electron density towards them, and the carbon is going to, in compensation, try and pull a little bit of the electron density from the hydrogens. So as a net result, this end of the molecule is going to be fairly negative, this end is fairly positive, and I have this polarity to the molecule, negative, positive. And this generates a dipole moment of about 2 dBi. In reality, molecules can go somewhere between about 0 dBi for nonpolar to about 11 dBi if I'm dealing with a truly ionic species. And once we have an idea where the electrons are, we can start predicting some extent of reactivity. So next time, we're going to be looking a little bit more in detail at these bonds we've been creating and try and figure out exactly what is the difference in between a single bond, a double bond, and a triple bond, and what practical importance does that have? Until then, take care.